Hi, my name is Tabison. Today we'll be looking at a two-phase simplex method. So, the two-phase simplex method, as by name, uses two phases. This is basically an alternative for the big M method, and it uses artificial variables and excess variables to standardize a simplex algorithm. So now, it's basically used, or by definition is used to work with greater than or equals to signs, and or greater than or equals to signs in linear programming. And the initial phase would be to eliminate the artificial variables that have been set up based on a greater than or equals to sign. And then once that's been eliminated, you get your first phase will become feasible. Once your first phase has become feasible, then you work the math as if you are doing a normal simplex or a normal simplex algorithm. And really that's about it. Let's try an example and see if we can't further explain. Cool. So now we can basically try and do an example to see what the theory covered in the mind map means. This is basically an objective function and its constraint, and we need to switch it to the forms that suit the two-phase simplex method. So if you remember, we said that if you have something greater than or equals to, then we would have to add slick variables and an artificial variable. And if it was in normal terms, we would just leave it the way it was, or we would just use a normal simplex process where we just add a slack variable. So let me just show you. So based on this, we would add, we would make the constraint x plus y minus s1 plus the artificial variable a1 and make it equals to 2. And based on that, we would apply what we use on a normal simplex process, and we would add s2 rather than having an artificial variable because it satisfies the normal process. And then initially we would look at the objective function, and we would have to look at that as if we were maximizing, and we would have to basically times everything here by 1, right? If we're looking at it as if it was a maximization, we would have to times this plus this by minus 1, actually. So in that case, we would have a minus z equals to, we would have a z is equals to 2x plus y. And for that over there, so now we would have these values, and this is what we would use in our table to perform our calculation. And basically we would populate these 0x plus 0y plus 0s1 plus 0s2 plus, minus a1 for our table. And those would be the values used to prepare you for the two-phase calculation, or rather your first phase in the two-phase process of the simplex algorithm. Cool. Let's go on further. Okay, so now that we've established the constraints as well as the new zj or z variables, we can plot them in the table. So basically, let me just zoom in. Since we know what our coefficients of the first constraints are, so coefficient here would be 1, coefficient there would be 1. We know S1 is equals to -1 in that case for that select variable, and then that would be 1. That would be 0 because there's no S2 there, and that would be 1, and our answer would be equals to 2. So we won't calculate this at the moment, we won't get the ratio. And for the second constraint, we know that that coefficient is 1, that coefficient is 1. There's no S1 there, so we make it 0, and then we add a +1 for S2. Sorry, I made a mistake there. And then for A, we don't have an A on the second constraint, so that will be 0, and this will be an answer of 4. And then I'll just write it up at the top. Let me make space. I'll write the objective at the top. Let's just put a line there. So make space there. Basically, we populate those objective elements there, -1. So emphasis will be on the artificial variable because that's what we're trying to get rid of to make it a feasible, or to give us a feasible objective for the first phase, so we can move on to the second phase, or to make this, or the constraint as well as the objective, feasible to go on to the second phase. So yeah, now in order to do that, basically we need to set up the table in order for us to eliminate A1 being an artificial variable, and that's what we see here. So let me make it smaller. And then the second one would be S2, which is second in line. And basically, what if we can get rid of A1, making the whole LP feasible, we would replace A1 with something else that follows the table, right? But we'll see that just now. So now the values for these would be, this would be -1, and that would be 0. Cool. Let's go on further. Okay, so now our aim is to get Zj, or this column here. So to do that, we would have to take our artificial variable, times it by the bases in the table, and plus it to S2. So that would be -1 times 1 plus 0 times 1 for S1. That will give us a value of -1. Same applies here, where -1 times 1 plus 0 times 1. That will give us -1 as well. -1 times 1 is 1. 1, 0 times 0, which will give us 1, right? And this will give us a 0. This will give us a -1. And that will give us a -2. Cool. Now to get this, we would minus Cj, or the original objective function, with Zj, which is the one we've created right now. So that would be that minus that. Don't forget your signs. So 0 minus 1 would always give us positive 1. 0 minus 1 will give us a positive 1. 0 minus 1 gives us a minus 1. And 0 minus 0 will give us a 0. And minus 1 over there, minus 1, that will give us a 0. Right. So now, since we're looking for the minimum or the max value, rather, since this is a minimization, we're looking at the maximum value, which is that, right? So we would highlight that column right there. So that column would be our pivot column, and then using the pivot column, we would establish the ratio being established by dividing the solution by the pivot column. So the solution in this case is 2, and the column would have a value of 1. So if you divide 2 by 1, you still get the value of 2, that's your ratio, and you divide 4 by 1, you get 4. So now there we look at the lowest positive value, which is 2, and we would highlight it like so. And our pivot value in this case, or pivot row, would be that, and this would be our pivot value 1. Okay, let's go on to the next. Okay, so because A1 was our leaving variable, so leaving variable would be the row in which, or your pivot row, and your entering variable would be your column. So in this case, because A1 was our leaving variable, we've eliminated it and replaced it with x1. So leaving variable means it's leaving the equation, or it's leaving the linear program. Now we replace it with x1, which is available, or rather x, sorry. And now our pivot would be equals to what we've established from the ratio, which are those values. Now, I think if you remember, once you've established your pivot, you'll subtract your columns. In this case it was 1, and you would subtract your pivot column, which was minus 1 at the time, which will give you equals to 0. So basically, aside from your ratio column or your pivot values, aside from your pivot, which would be equals to 1, or your pivot point, which would be equals to 1, all the fields above the pivot point need to be equals to 0. And that's basically what we've done. So now that we've established the value of 1, which is that right there, all of these are zeros. So since we've found that, we've recalculated ZJ like we did before, and we found that it's equals to 0 because we're timesing everything by 0. So those are the values that you're timesing by, and everything will give you 0. So now if you take the original CJ and you minus it by ZJ, you'll get these values. And as per stipulated by the current LP that we're working on, you're only supposed to get 0 and below for maximization, right? So this is less than 0. So therefore, we've satisfied that, because this is 0, that's 0, that's 0, that's 0, and this is below 0. So A1 is less than minus 1, or rather less than 0. So we satisfy that, and we can move safely into phase 2. So phase 2 is basically the normal simplex method, where you work with the current objective function and the constraints specified. So you can just simply plug in the original objective function in to work with it. Alright, cool. Thank you. That's about it. Cheers, bye.